Besides these structural issues, there are additional challenges when moving ML models into production. After building and training the model, there are still numerous tasks to tackle, starting with packaging. Once the model is built, it needs to be compiled, packaged, and all dependencies must be resolved, which may require running specific scripts. Another critical consideration is performance. Training a model on large datasets can take hours, or even days, for a single run. Performance adjustments may involve scaling, load balancing, data partitioning, parallelization, and GPU support. For instance, if we're using the model for real-time fraud detection in credit card transactions, it needs to make predictions in milliseconds to avoid delays. Here, our model must be robust and highly responsive to handle high volumes of data without adding latency. Moving on to another crucial aspect, versioning in machine learning goes beyond traditional software. In machine learning, it's not just code that needs versioning, but also data, algorithms, parameters, and even the training environment. Each combination of data and parameters can create a different model version. Imagine a client asks you to redeploy a previous model version, but detailed version records haven't been kept. This scenario can be a challenge, especially if key team members who worked on earlier models have left the project. This highlights the importance of having a solid versioning mechanism for all entities, from data and algorithms to parameters and environments. Now let's talk about monitoring. Monitoring is crucial, not just for tracking accuracy, but also for keeping an eye on data quality and detecting drift. After deployment, we need to ensure that the data patterns remain as expected, or the model's accuracy could degrade. Additionally, ML systems require latency monitoring, health checks, memory usage tracking, and system-wide metrics. Without robust monitoring, we might only receive feedback from end users, which is often too late. Lastly, there's the question of automation. In the traditional ML lifecycle, tasks like data versioning, model training, validation, and monitoring are mostly manual, which consumes a lot of time. Once deployed, models inevitably degrade in accuracy over time and require retraining. Retraining demands that we repeat the entire lifecycle, a time-intensive process that could strain client relationships if models are left underperforming for extended periods. To wrap things up, machine learning projects often accumulate a substantial amount of technical debt. This complexity involves significant infrastructure, resource management, and monitoring. Google has published a widely recognized diagram illustrating the hidden technical debt within ML projects, highlighting that the actual model code is only a small part of the larger ML ecosystem. In the current landscape, data scientists and engineers spend much of their time managing infrastructure and operational tasks, making machine learning one of the most multidisciplinary and cross-organizational efforts within companies today. Without a standardized approach, each team tends to manage ML deployments in its own way, which might work for small-scale projects. But as the industry grows, the demand for scalable, automated, and streamlined ML deployments is increasing. Without these systems, ML models risk being confined to experimental phases, unable to transition into production. So to sum up, transitioning from model development to deployment does take a lot of time and is a significant challenge for enterprise ML projects. I hope this discussion has clarified the challenges in the traditional ML lifecycle. In the next lecture, we'll explore how MLOps addresses these issues, bringing much-needed flexibility and automation into the process. Stay tuned.